Have you ever watched a movie or, a TV show and seen a character just seamlessly lifted out of a scene, maybe dropped into a completely new background or just isolated perfectly? It's that kind of visual sleight of hand, that Hollywood special effect where the foreground it just pops from the background.
Right.
But getting that perfectly right, making it look completely natural, stable across hundreds, maybe thousands of frames, that's not just tricky.
No, it's a really profound technical challenge.
Exactly. So how do you make the invisible visible and then make it move flawlessly? Okay, let's unpack this.
Indeed. What you're describing there is the visual magic of video matting.
Mm.
At its core, it's really about extracting a foreground object from a video, pixel by pixel, and determining not just what is there, but also how transparent it is at every single point.
Okay, the transparency bit, that sounds key.
It is. That transparency information, the subtle details like individual wisps of hair or maybe the translucent edges of a glass, even soft reflections. That's what we call the alpha matte.
Alpha matte, got it.
The problem is, for computers, this is what we often call an underdefined problem.
Underdefined, meaning?
Meaning the system isn't always sure what specific object you actually want to isolate or exactly how its edges are supposed to blend. So traditional methods, they often struggle with, say, complex or ambiguous backgrounds, blurry boundaries, or results that just flicker distractingly from frame to frame.
Right, that flickering really breaks the whole effect.
Completely.
And that's precisely where this groundbreaking system called MatAnyone comes in. This isn't just like a small step forward. It sounds like a significant academic breakthrough.
It really is. It tackles these deep, technical, and I'd say theoretical challenges head on.
So our mission in this deep dive is to explore exactly how MatAnyone achieves these, really impressive, stable, high-quality results, especially in human video matting. We're going to try and dissect the innovative core of this system, understand the nuanced academic insights that make it so powerful.
That's good.
So, to start, if MatAnyone is our hero here, what exactly are the dragons it had to slay? What makes video matting such a thorny problem in the first place? We're not just talking about cutting out a basic shape, right?
Not at all, no.
We're talking about capturing that subtle transparency, those incredibly delicate edges, and somehow maintaining perfect consistency across potentially thousands of video frames. That sounds hard.
That's an excellent way to frame it.
Yeah.
The difficulty really stems from several fundamental limitations in the existing approaches.
Yeah.
People have tried different strategies. First, you have what are known as auxiliary-free methods.
Okay, auxiliary-free.
Right. These models rely only on the raw input video frames themselves. No extra guidance like a user-drawn mask or anything.
Oh, okay.
The core issue there is they often lack a clear target. I mean, imagine a person standing in front of other people or against a really busy textured background.
Right. How does it know which person you want?
Exactly. An auxiliary-free method might easily get confused. It struggles to isolate only the target person, and that leads to uncertain results and, crucially, poor temporal consistency.
That flickering again.
Or the object's shape seems to subtly morph frame to frame, which immediately breaks the illusion.
Okay, so auxiliary-free has its limits. What else?
Then you have mask-guided methods. Now, these seem more robust initially because they use a segmentation mask.
Which is like a rough outline.
Yeah, basically a rough outline of the object you want as a starting point, so it has some guidance.
Okay, that sounds better.
It does, but this approach hits a different wall. It's significant data limitations, which, is a common bottleneck in AI research.
Ah, the data problem.
The data problem. Take the widely used VideoMat 240K dataset, for example. It actually has some serious quality issues. The research points out problematic semantic accuracy in core areas, meaning the model often misidentifies the identity of pixels within the object itself. So you get things like interior holes, where the system thinks part of solid object is actually transparent when it absolutely shouldn't be.
Oh, okay, that's not good.
No. And critically, it also lacks fine details along the boundaries. So you end up with blurry hair or fuzzy edges instead of those crisp, realistic ones you need. And these problems often stem from things like reflective regions on clothing causing spurious holes in the alpha mats, or maybe inconsistent transparency levels in core regions because of shadows or just noisy backgrounds in the original green screen footage.
So even the supposedly good data we have for training isn't really good enough. Is that a common thing in AI where the data itself becomes the bottleneck, maybe even more than the algorithms?
Precisely. It's absolutely a recurring challenge across many AI domains. And on top of those quality issues you mentioned, video matting datasets are also just much smaller in scale compared to something like video object segmentation, VOS datasets.
Right, VOS datasets are huge, aren't they?
They are, and they're excellent at just detecting objects. Plus, the matting datasets are largely synthetic.
Meaning models trained on them might not work so well in the real world.
Exactly. They often don't generalize well to the messy, unpredictable complexities of real-world video. And what's more, there's this fascinating, almost paradoxical problem. If you take strong VOS models, which are really good at semantic understanding, knowing what an object is, and you try to fine-tune them with this existing lower quality matting data.
You'd think it would make them better at matting.
You would think. But often it actually disrupts this prior.
Disrupts the prior.
Yeah, I mean, it's the matting data, instead of refining the VOS model for matting, actually makes it worse at its core object recognition task.
Wow.
Which leads to unsatisfactory matting quality overall. It's like the bad data confuses the good model.
This really highlights something important then. Matting isn't just about semantic detection getting the main shape right. It also needs this incredibly high-quality detail extraction along the boundary, like you said, individual strands of hair. That's a much, much higher bar than simple segmentation, which is often okay with just a hard, crisp outline.
Absolutely. It demands both accuracy of identity and subtlety of transition. It's a dual challenge.
Okay, let's unpack this then. How does MatAnyone address these really deep challenges? You mentioned it uses a target-assigned approach.
That's right. Target-assigned video matting. So you provide a mask, that rough outline, just for the first frame.
It's just the first one, not every frame.
Just the first one. And then the system is designed to consistently track that specific object throughout the entire video, no matter how long or complex it gets.
That's a huge practical advantage.
It is. And this is where it gets really fascinating from an academic perspective, because it's built on what's called a memory-based paradigm.
Memory-based, so it's designed to remember your target.
Precisely. It needs to hold on to what it's supposed to be matting. And the first key innovation here, a significant academic contribution, is what they call consistent memory propagation, or CMP.
Okay.
And they achieve this via something called region-adaptive memory fusion.
Region-adaptive memory fusion, that sounds complex.
It's clever. The problem they identified with standard memory matching techniques in video processing is that they tend to assume all parts of an image are equally important when propagating information from one frame to the next.
But that's not true for matting, is it?
Exactly. In video matting, the significant changes in alpha values where transparency shifts, from opaque to transparent or vice versa, primarily occur at the boundaries of an object, not usually in its stable, solid core. The core should generally stay opaque, the background transparent, and it's mostly the edges that need careful handling frame to frame.
Right, the action is at the edges.
The action is at the edges. So MatAnyone introduces a boundary area prediction module. This module essentially estimates a change probability, which they denote as UR, for each little pixel or token.
A change probability, yeah.
Yeah. If UR is high, it signals a large change region, like a moving boundary, maybe hair blowing in the wind. If UR is low, it indicates a small change region, like the stable core of the person's torso.
Okay, so it figures out which parts are likely changing and which are stable.
Correct. Then the system performs a sophisticated soft merge. You can kind of think of it like this. MatAnyone constantly asks itself, how much of what I'm seeing right now is truly new information at the boundary, and how much is just the same stable object I saw a moment ago in the core?
Ah, okay.
And it blends its current observation queried from a memory bank with values propagated from the last frame. But here's the really clever part, the academic elegance.
Yeah.
It uses that change probability, our UR, to decide how much to blend.
Ah, so it weights the blend based on predicted change.
Precisely. If UTS is high, boundary region, it prioritizes the new information, focusing on getting those delicate edges right. If UTS is low, core region, it relies more on the propagated memory, what it already knows is stable.
It's like a dynamic trust system for pixels.
That's a great way to put it. This adaptive weighting based on predicted change is key.
That is a super elegant way to handle both the stable parts and those constantly changing edges. It ensures the system knows where to be rock solid and where to be delicate and adaptable.
Exactly.
Allowing it to maintain both consistency and fine detail at the same time.
This region adaptive approach is absolutely crucial for stability. In the core regions, it ensures internal completeness, no weird holes, and a perfectly clean, consistent background removal. Then, in the boundary regions, it intelligently focuses the network's attention on those delicate, soft alpha values. This prevents semantic errors where it might misinterpret the edge, and it also stops that frustrating flickering across the video frames.
Yeah.
It's about being robust where it needs to be, and incredibly precise where it really matters for visual fidelity.
That's incredible. But okay, how do you even train a system to be that precise when, as we just discussed, really good, clean data is so hard to find in this specific domain?
Yeah.
You're asking the model to perform at an extremely high level, but the traditional training grounds are, well, full of potholes, as you said.
That's the million-dollar question. And it brings us to their second major innovation. And arguably, this is one of the most significant academic contributions of their work, their new training strategy. Specifically, they call it core area supervision via segmentation.
Okay, core area supervision via segmentation. Let's break that down.
So the core problem, as you highlighted, is that real video matting data is scarce and often pretty low quality. Prior methods, they often use separate heads in their neural network architecture. One part, or head, for general segmentation, and another part specifically for matting.
Okay, two different jobs.
Two different jobs, processed somewhat separately. This meant the matting head didn't get direct supervision from the vast amounts of real segmentation data that already exist and are quite good.
So it wasn't learning from the better data available for just finding the object shit.
Exactly. And that led to a fundamental semantic instability in the final matting results. It was kind of like trying to teach someone two related skills, but using completely disconnected lessons and materials.
Got it. So how does MatAnyone fix that?
MatAnyone takes a unified approach. It directly supervises the matting head itself with large-scale real segmentation data.
Okay. It uses the good segmentation data to teach the matting part about object shapes.
Precisely. The matting head is trained to predict the alpha mat, even for these segmentation inputs, and it optimizes itself based on that. Then, they apply what are called region-specific losses. Losses are just mathematical functions that measure the error the model makes, which it then tries to minimize during training.
Okay, different rules for different parts of the object.
Kind of. For the core regions, the stable middle parts, they use a relatively simple pixel-wise L1 loss.
L1 loss.
Yeah, it basically just means it wants the predicted pixel values in the core to be as close as possible to the true values, pixel by pixel. It's straightforward, robust, and ensures the core of the object remains semantically stable and generalizes well.
Okay, that makes sense for the stable core. But what about those critically important, really tricky boundaries? How do they get the fine details right there?
Yes. This is where it gets even more fascinating and really highlights their deep academic insight into the problem. For the boundary regions, they use an improved version of a loss function called scaled DDC loss.
Scaled DDC loss. Okay. What was the issue with the original?
The aha moment here was realizing that the original DDC loss, which was pretty standard in the field, made a crucial but often untrue assumption. It assumed that the difference between the foreground color and the background color was always stark, like a value of 1.
But that's not always true in real photos, right? Edges can be blurry or have similar colors.
Exactly. That simplifying assumption caused the model to produce segmentation-like jagged and scarce-stepped edges for the alpha mats. It wasn't creating the smooth, realistic, continuous transitions you need for natural transparency.
Okay.
So their improved scaled DDC loss directly accounts for that actual, often nuanced, foreground-background color difference that exists in real images. This modification, which came from a deeper understanding of the image formation process itself, yields more stable and natural matting results because it allows for a much more accurate representation of how foreground and background actually blend at the edges.
Wow. That's a fundamental correction.
It is. It elevates the scientific rigor significantly.
So they're basically telling the network, okay, for the middle of the object, be solid and consistent, like segmentation tells you. But for the edges, be subtle, be realistic, pay attention to the real color differences, like a true alpha mat should.
That's a perfect summary, yes. Marrying those two different requirements into one cohesive training system.
That's incredibly smart.
And there's one more clever trick they incorporate, this time for inference, that is, when the trained model is actually used on new videos.
Okay.
It's called recurrent refinement. During inference, optionally, they can warm up the first frame.
Warm up the first frame. How?
It means the very first frame of the video is actually fed into the system multiple times, repeatedly. Each repetition serves as like an initial input, The alpha mat output from, say, the final repetition then initializes the alpha memory bank that the system uses for processing all the subsequent frames of the video.
Huh. What's the practical benefit of doing that? Just repeating the first frame?
It seems simple, but it's effective. This technique significantly enhances robustness against the given segmentation mask. Remember that initial mask you provide, even if that mask is a bit rough or imperfect.
Okay, makes it less sensitive to a bad starting mask.
Exactly. And crucially, it also refines matting details in the first frame to achieve image matting quality.
Ah, so it gets the first frame looking really good before moving on.
Right. It sets up the entire rest of the video for higher quality, more consistent results right from the absolute beginning. It minimizes the chance of propagating any initial errors down the line.
That makes sense. A pragmatic but scientifically sound way to improve the starting conditions, especially for potentially long videos.
Precisely.
Okay, so all this brilliant engineering and really deep academic innovation needs high-quality fuel, right? It needs data.
Mm-hmm.
And it sounds like MatAnyone didn't just build a better engine. They understood that to truly excel, they also needed to build a better road for it to drive on. They really overhauled the data sets.
Absolutely. This emphasis on data quality and quantity is another cornerstone of their academic contribution. You can't separate the model from the data it learns from. They introduced two crucial new data sets. First, there's VM800, which is their new training data set.
VM800.
It's significantly larger, twice as large as the previous standard data set, VideoMat 240K. We're talking 826 foreground videos compared to 475.
Okay, double the size.
And maybe more importantly, it's far more diverse in things like hairstyles, outfits, and motion, because they sourced it from professional video footage websites, not just limited academic collections. They used high-quality 4K green screen videos. And here's the key aspect, demonstrating their meticulous academic process. They performed careful manual selection.
Careful manual selection, meaning humans looked at it.
Yes, humans look very carefully to remove common artifacts that plagued those older data sets we talked about earlier.
So they're not just getting more data, they're getting painstakingly cleaner data. What kind of artifacts were they actually weeding out? That sounds like a lot of work.
It was undoubtedly a huge amount of meticulous work. This careful manual selection wasn't trivial. We're talking about potentially human experts scrubbing through thousands upon thousands of frames. They were looking for those subtle issues, like maybe a shiny piece of jewelry on the subject. Older data sets might misinterpret its reflection as a transparent hole in the alpha mat, which is wrong. Or a subtle shadow on the green screen could cause inhomogeneous alpha values, inconsistent transparency levels in core regions that should be perfectly solid opaque.
Things a human might notice, but an automated process might miss.
Exactly. These subtle, human perceptible flaws, if you leave them in the training data, they essentially poison the model training. They lead to those problematic inference results we discussed. So VM800 significantly boosts both the quality and quantity of training data by diligently removing this noise. It's about data hygiene at scale.
Okay, so VM800 for better training. What was the second data set?
The second was YouTube Mat, which is a new synthetic benchmark dataset used for testing and comparison.
YouTube Mat.
This provides 32 distinct 1920 by 1080 green screen foreground videos sourced directly from YouTube. It's over 6 times larger than the previous benchmark.
6 times?
Yeah, making it a much more representative benchmark for the kind of content people actually encounter or want to work with, crucial for academic validation against real-world-like data.
And is it just bigger, or is there something else special about it?
It's also more challenging. It applies harmonization during the process of composing the foreground onto a new background.
Harmonization? What's that?
It's not just crudely slapping a background image on. It subtly adjusts the colors and lighting of the foreground subject to make the composite look more natural and realistic, as if it were actually filmed in that new environment.
Blending it better.
Right. It mimics real-world lighting complexities. This makes it a more challenging benchmark that is closer to the real distribution of images you'd find online. And it can actually confuse older, less robust matting methods.
Okay, that makes sense for testing robustness. But how do they evaluate performance in real-world scenarios? You know, where you don't have a perfect ground truth alpha mat like you do with green screen data.
That's another clever part of their scientific methodology, tackling a common evaluation problem. Since real-world videos lack those perfect alpha mats,
Right.
they leverage other high-precision methods, specifically video object segmentation methods like one called Qingyi, to generate very accurate frame-wise segmentation masks.
Okay, so not alpha mats, but really good outlines.
Exactly. These highly accurate segmentation masks effectively act as a kind of ground truth, but only for the core areas of the objects. You can't use them for the fuzzy edges, but you can use them to check if the core is solid and correctly identified.
I see. So they can measure how well the model handles the main object shape and avoids holes or errors within the object, even on real videos.
Precisely. This allowed them to rigorously evaluate semantic stability and generalizability in challenging real-world videos, using standard metrics like MAD, mean absolute difference,
Right.
MSE, mean squared error, and DTSSD.
Okay, standard error metrics.
Right, applied to the core region. It provides a robust measure of real-world performance, even when a perfect alphamat isn't available for comparison. It's a pragmatic approach to real-world validation.
So, okay, we've got these incredible innovations, the region adaptive memory, the new training strategy with core supervision and scaled loss, the inference refinement, plus these much better data sets. What kind of results does MatAnyone actually deliver? Do all these ingenious academic insights and hard work truly translate to superior real-world performance? Or are they just, clever theoretical constructs?
Well, the proof is absolutely in the pixels, and the quantitative numbers back it up strongly. On the synthetic benchmarks, like that challenging YouTube MAT dataset at full HD 1920 by 1080 resolution, MatAnyone achieves the best AMA and DTSSD across all datasets.
Best mean absolute difference in temporal stability.
Exactly. MatAnyone reflects the spatial accuracy, how precisely the pixels are cut out. And DTSD measures that temporal stability, how little flickering or shape change there is between frames. Just to give you an idea, on YouTube MatAnyone gets a MANA score of 1.99 compared to a previous state-of-the-art method called Maggie, which scored 2.37. Lower is better here.
Okay, that's a noticeable improvement.
It is. And for MSE, another error metric, MatAnyone gets 0.71 versus Maggie's 0.98. Again, lower is better. It also scores best on something called CON, which relates more to the perceived visual connectivity and quality of the map.
So across the board on synthetic data, it's showing exceptional spatial accuracy for alpha mats and remarkable temporal stability.
That's what the results indicate, yes.
But what about the real-world benchmark? That seems like the ultimate test.
And that's where the difference is perhaps even more striking, highlighting its academic rigor translating to practical generalizability. On their real-world benchmark, using those core area metrics, MatAnyone vastly outperforms the others. It achieves a MEDI score of just 0.14.
0.14. Compared to what?
Compared to RVM Large, another method at 0.95, or Maggie at 1.94.
Wow, that's not just better, that's like an order of magnitude better.
It's a substantial margin, yes. It's a clear indication of its superior performance and ability to generalize to complex, unseen real-world scenarios.
That's a huge leap in the quantitative metrics. What does that actually mean for the visual quality you see? Like, if I use it, what's better?
Qualitatively, you see the difference. MatAnyone really excels at capturing those fine-grained details, like accurately rendering individual strands of hair, which is notoriously difficult. It can precisely distinguish a full human body from incredibly complicated backgrounds, even when the foreground and background colors are very similar. That's a classic matting challenge.
Right. Separating similar color.
And what's also particularly impressive and demonstrates its robustness in practice is how well it handles instance video matting.
Instance video matting.
Meaning it can consistently track a specific target object, say you in a crowd, even when other similar objects like other humans are moving around in the scene.
And it doesn't get confused and start matting the wrong person.
Exactly. It stays locked onto the target instance you specified with that first frame mask.
And crucially, just the first frame mask, you don't have to keep telling it which person is which.
Correct. Many other methods would require you to provide masks in multiple frames, or even every single frame for complex scenes, which is incredibly time-consuming and, frankly, impractical for most users.
Yeah, totally impractical. And I assume the ablation studies where they tested the impact of each innovation by removing it one by one confirmed how crucial each component was. It wasn't just one magic bullet.
Precisely. Those ablation studies are vital for scientifically validating the specific contribution of each proposed innovation. They're a cornerstone of rigorous academic research in this field. And yes, they show that every piece of the puzzle contributes significantly to the final performance. For example, when they removed their novel scale DDC loss and went back to the original DDC loss, the results reverted to showing that segmentation-like jaggedness at the boundaries,
Okay.
whereas including their scale DDC loss yielded the more stable and natural matting result.
So it directly proved the value of that specific loss function change.
Yes. Similarly, training without their new, cleaner VM800 dataset noticeably impaired the semantic performance and the overall robustness of the model across all benchmarks. It truly demonstrates that it's the synergy of all these academic insights, the architecture, the training strategy, the loss functions, and the high-quality data that leads to such powerful and reliable results.
So if we connect all this back to the bigger picture, MatAnyone really isn't just, an incremental improvement in video matting. It feels like a significant leap forward for the field.
I would agree.
It's shaping up to be a genuinely practical solution for complex real-world scenarios. And it all stems from these ingenious academic insights and that meticulous engineering we've discussed.
Absolutely. It really showcases the power of applying deep theoretical understanding to tackle a fundamentally hard problem. The ability to reliably track and mat a specific target object in long, complex videos using just that single initial mask, it really does lay a solid foundation for future research in memory-based video processing of related areas. It proves that by deeply understanding the nuances of the problem, the physics of light and transparency, and the inherent properties and limitations of the data, we can create surprisingly robust and accurate AI systems that achieve a level of fidelity that was previously thought to be incredibly difficult, maybe even impossible, just a few years ago. It's a real testament to the power of dedicated academic inquiry driving practical progress.
Which I think raises a really important final question for you, our listener. With this kind of technology becoming available, with this level of precise, stable video matting now potentially within reach, what could you create? Could it revolutionize how we interact in virtual spaces, maybe for meetings or social VR? Could it empower completely new forms of content creation for everyone, from indie filmmakers to educators to, social media creators? Or could it even fundamentally change how we analyze complex video data for scientific research, perhaps in biology or physics? Think about the possibilities this level of precise visual control unlocks. What new ideas does it spark for you?